some computers can grab and get half the headline. Really, they're very specialized about but it's true that with quantum programming, it's really this is the model that makes sense. It's called the qubit. but the other aspects it really most valuable. Conditional is what you can quantum control. So if you have to have one, how does that have no basic? I want to stress that these 5 steps that I gave at the top are not how good the algorithm is used, how good the algorithm is used. Look at how good the algorithm is usually implemented in terms of the corporate knowledge. And this is kind of low level, the drawback. Seldom low level in textbook and with algorithm. If you are looking at actual code, which algorithm and one thing that's the assumption here is that you use the access. You cannot have access. If you want to analyze something, right? Exactly what I'm saying, like this slide in the real estate. Kind of proven a lot. A few different operations. Really, take my word for it. Really, what I was trying to really want to stress this, this is not how we're used to thinking about functions with F. We want to put that output to the happen. That we're forced to deal with this use of F. This is not how we deal with the condition. We're assuming that that means something specific.
The deferred measurement principle to convert it into a nicer form. If your implementation of F is only approximately implemented, it's even harder because then you have to figure out how that approximation affects the accuracy of Deutsch's algorithm as a whole. So this is kind of a common thing in quantum algorithms, bounded narrow quantum subroutines. This is something that quantum algorithms people assume they classical aspects that approximate f of x given x. Then you can convert it into this nice reversible form that that matches the form that we need for Voichick algorithm. But actually doing this conversion is not trivial in existing languages. It's not particularly difficult, it's just tedious, and it really feels like something that the compiler should be doing for you and it should be built into the language semantics. This is, I guess, as a more concrete example of where this is used. The triangle finding algorithm is one example where this is kind of critical. This is an algorithm that finds whether there is a triangle in an arbitrary graph. And it depends on this reversible oracle for a separate problem, the element distinctness problem. Now, quantum computers also give an advantage for this element distinctness problem. And so if you look at how this element distinctness problem is implemented, it'll look something like this. And you'll notice that this is not in that nice reversible form. It's actually, it depends on yet another reversible oracle for F. And so this is kind of, if you read the papers, this is not something that they state explicitly. They're kind of assuming that you have it in a nice form. And so this is really something that should be built into languages, in our opinion. And this is something that Qunity does pretty well, because we allow this subprogram F to be an arbitrary quantum algorithm. So what does this give us? So in our paper, we talk about kind of four main contributions. There's the Qunity language design. There's the well-specified behavior of this language, including a type system and a denotational semantics. We also prove a few properties of this language and describe how it can be compiled into lower-level circuits. So the first principle of the language is generalization of classical constructs. And the main benefit to this is that any classical programming just works when applied to quantum data. I guess you only need to write one addition program or one of any classical algorithm. You don't need to write a separate implementation for the part that's running on quantum hardware. And I guess for this argument to be justified, we kind of need to show that this classical sublanguage, which up here is reasonably expressive. And we do prove this in our paper. We prove that any program written in a more typical classical let-based language can be translated into Qunity in a way that preserves types and semantics. We use this specific language from a paper of James and Saber 2012 because its type system encodes reversibility in a way that translates nicely into Qunity, but it's a fairly typical looking language, so first order classical functional language. And so for this approach to work, we also need to, I guess if we have fairly expressive classical sublanguage, there's a challenge in figuring out what is the quantum interpretation when you generalize from quantum to classical. And so we have a few interesting things that we're doing. Not all of these are completely novel, but I think the combination, some of them are novel and the combination pattern matching, for one, that is used to implement quantum control, which we saw in Deutsch's theorem. We also allow for non-exhaustive patterns, which are a kind of quantum assertion, or as physicists would describe it, a projector. We're able to couch these assertions as a kind of exception handling syntax, and that is something that physicists would describe as a projective measurement. We also allow for variable reuse, like you would expect to see in a typical classical language. A lot of quantum languages disallow this because of the no-Clummic theorem. We allow it, we just treat it as an entanglement operation. So in terms, if you're interested in substructural types, this is kind of an interesting point in the design space because we're using relevant types where variables are used at least once, rather than affine types where variables are used at most once. We also allow some types, just for more useful data structures, because you want those sum types in a classical setting. So, and I guess we have an example in our paper where it's useful in a quantum setting as well. Our type checker for this language is verified within the clock proof system. So you can play around with it if you like. Our denotational semantics is compositional, and as I explained before, what's more interesting, I guess, is that it allows for composing programs in useful and interesting ways. We also prove in our paper that this semantics is, in fact, well defined because our technical definition is not obvious, but we can prove this. And finally, we want Qunity to be realizable on actual quantum hardware. So we're using this kind of nice generalization approach, but when we want to run Qunity programs, we kind of need to adapt it to the existing models, the existing assembly languages. And so we describe in our paper how this compilation can be done, converting Qunity programs into lower level quantum circuits. And we show that the behavior of this compiled circuit matches Qunity's semantics. As potentially interesting future work, it would be interesting to make this compiler a little bit smarter and compile the classical sublanguage to classical hardware. Right now, we're not doing that because it's simpler to just make everything quantum. That will not be efficient for running actual large-scale algorithms, but interesting potential future work. So to summarize, I presented Qunity, motivated by wanting an expressive generalization of classical computing. We have its type systems, semantics, theorems, and composition. So thanks for your time, and I'll take any questions.
We have time for a few questions. Yep.
Thank you for the very interesting talk. So you mentioned earlier that one might want to write a classical program like an add-on and have such a program also work well for quantum data. In practice, you might also want to specialize this sort of program because certain forms of adders just tend to be more optimized under a certain gate set for the quantum program. So can you speculate on how we might be able to reconcile those kinds of customization choices with a design Qunity?
Yeah, so you're right in that these different kinds of hardware are good at solving different problems. And I guess a kind of hand-wavy answer is that this is the compiler's job. The future compiler should be smarter about figuring out what parts of it are classical and should be compiled to classical hardware. But currently, we're not really targeting super efficient compilation.
Thank you.
Any questions?
Hi, this is Maria from University of Sussex. I was just wondering if you could tell us more about the denotational semantics, also the structures that you use, usual field spaces or...
Yes, so I guess roughly, I mean, I mentioned some types earlier. So basically, our language has sum and product types, which semantically correspond to the direct sum and the tensor product of Hilbert spaces. Our operators, well, so our programs, I guess what I didn't, I guess we have this classical sublanguage, but there's also a reversible sublanguage. The type system has a reversible subtype. And so these reversible programs, the semantics will be an operator, and the more general class of programs will have semantics of a super operator, like a CBT map.
This is kind of already been asked, but what do the common folks think about this? I mean, does the language keep them from saying something they want to say, or the realization keeps them from doing the optimization they want to do?
I think, I mean, I guess I've talked to some quantum people who are interested in this. I guess the problem is it doesn't really solve the near-term problems. So I guess, I mean, it is expressive enough to express algorithms with the asymptotic complexity that you want. But I guess near-term quantum programs are going to depend on very low-level gate optimizations, and that would require if you want to do that in Qunity, it would require a very good compiler.
I think it's better to switch to the next talk, which will be given online, but beforehand,